All right. Good morning, everyone, and welcome to this week's coffee break. I am Brandon Pappas, and today we have Einar Frobaum joining us to discuss chilled beams. Take it away.
Awesome. Thanks, Brandon. Appreciate it. So as Brandon said, my name is Einar Frobaum. I'm the Director in Sales and Marketing for Carson Solutions. And Carson Solutions is a manufacturer of various style chill beams and induction units. And predominantly we'll be talking about active style chill beams and why we see them as a ripe fit for what we see as a resurgence in the HVAC market. So a couple things that I want to make sure we understand as we step through this presentation today is why the potential and what we see as a resurgence for chill beams, various style and different variations of chill beams, how do chill beams, particularly active chill beams, function, what are the type of the mechanical systems that integrate chill beams, and then if we remember the why, the potential, we'll start talking about and seeing the benefits for applying chill beams. When we look at occupied spaces and we look at designs addressing occupied spaces, what I have on the screen here is what I feel good cross-sectional representation of the things that are important to the end user: air quality, acoustics, thermal comfort, aging infrastructures oftentimes. And I think one of the biggest things that I see is how do we deal with the increased demands for energy efficiency and not overcomplicating or compromising the budgets. So some of the reasons, the key reasons why I see the opportunity for chill beams being a good fit is in response to the continued increase for code required efficiencies, understanding that heating and cooling with hydronics is much more efficient than an all-air system. DOAS units are smaller than an all-air air handler. Indoor air quality has gained greater awareness within the HVAC industry and general public. And then certainly there's industry and market pushes for electrifications where we might start seeing geothermal and heat recovery approaches being a very viable solution. So, variations of chill beams. There's two predominant styles. One is a passive beam, and it sort of, as its name implies, is passive. It doesn't have an outside air source that's delivered to it. It acts as a radiant cooling device. It relies on the warm, buoyant air moving upward until it comes in contact with the cooled surface. And then once that air becomes cooled, it then drops down due to the buoyancy relationship within the space. And it's suitable for light cooling load spaces, and it's not a viable option for heating within those spaces. On the other hand, active chill beams, they are active or activated by a primary air source being delivered to the beam that creates a venturi or an induction process, which helps with increased cooling loads and certainly a viable option for heating applications as well. And then you see what in the right-hand corner is a floor-mounted chill beam, and there's other styles such as soffit chill beams as well. Along those lines of different types of chill beams, what you see here in the upper portion of the slide is you have a two-way throw chill beam throwing supply air out two directions, and those are suitable for 2-pipe or 4-pipe applications. You can get those in 1 foot and 2 foot wide variations. And then you have what's in the middle of the screen, which is a one-way throw. It only throws in one direction, again suitable for 2-pipe or 4-pipe, exposed mounting or in ceiling mounting, also in 1 foot and 2 foot width dimensions. And then there's also 4-way throw chill beams as an option, and those throw, as their name implies, both east and west, as well as north and south, depending upon the application and suitability. How do active chill beams function? So what you have on the screen is you have cooling on the left, heating on the right. and you have primary air, outside air, 100% outside air being delivered to this plenum. In cooling, that outside air is somewhere between 50 and 55 degrees, and in heating, it's somewhere between 60 and 65 degrees. And as that plenum gets pressurized up to about a half an inch of pressure, it causes air to go out a series of nozzles, which creates a Venturi effect, which is a low pressure environment that pulls in or induces room air across a hydronic coil. And in cooling, we are typically feeding that hydronic coil with elevated chilled water, and in heating, moderate warm water. And as that room air then mixes with the fresh air, we get supply discharge out to the space. In cooling, somewhere between 62 and 64 degrees, and then heating somewhere between 82 and 85 degrees. So here's a video of typical operation of a overhead chill beam. Cling that air as it comes out of the diffuser. It clings to the ceiling via the Kawanda effect until it comes in contact with a wall or an adjacent airstream, and pushes that air slowly into the space until it comes in contact with a heat source, which then delivers that warm, buoyant air back up to the chill beam to return the process. So what type of mechanical system typically integrates chill beams? It is a DOAS or a decoupled system. Here you see on the screen a 100% outside air unit that is either preheating or pre-cooling, dehumidifying that outside air, handling the ventilation load, and more importantly, the latent load of the occupants. And now we have a verifiable, quantifiable amount of outside air that's properly dehumidified to allow the terminal device to be purely sensible. So that is a more elaborate schematic that you see on the screen. Here is your 100% outside air unit delivering fresh air down the corridor, feeding fresh air, primary air to these displacement chill beams in the typically classrooms for school example, and then maybe delivering 100% outside air to chill beams, overhead chill beams in, say, libraries, conference rooms, office spaces. And then you see oftentimes a chiller and a boiler integrated to produce the respective water medium supply. So remember the why and the benefits that we receive by applying chill beams: energy efficiency, thermal comfort, acoustics, maintenance. So why? Water is just a much more dense, more effective medium than air for handling the BTUs within the space, and moving air with a fan is not as efficient as moving water with a pump as well. So almost there. And then if you look at the air handler design, an all air handling design typically is much larger and needs to deliver cooler air to heat and cool the space. And then you have a large portion of return air that has to be handled. So the ductwork is large as well. And then you have to return that air back to the space, deal with it, and then circulate it again back to the space. Compare that to a DOAS-based system where the air handler is 1/3 the size, much smaller, delivering just the ventilation air to the space. Typically, there's a recirculation or entrainment at the terminal device where that supply air is then delivered to the space and then ultimately exhausted. And now we recapture that energy. But the takeaway is we have a smaller air handler, smaller coils, smaller electrical requirements. We have smaller ductwork, and we have no cross-contamination from room to room with a DOAS system. Now, if we take a look at what's on the screen, we have that same building schematic. And what if we want to pursue an electrified solution, either heat recovery chiller or geothermal, and eliminate that fossil fuel burning boiler? Now, if we go down that path, we immediately check the box for qualification of the Inflation Reduction Act, 30% top line tax credit plus modified accelerated depreciation as well. So thermal comfort, oftentimes we have localized spots that are too cold or too hot. And unfortunately, oftentimes what we see in the lower right-hand corner is a single point source of HVAC equipment, fan coil, unit vent, sometimes overhead diffusers. But the only way that those localized devices can treat the space is with high velocity and big delta T, both in heating and cooling. And that is where you unfortunately get drafts. Compare that with a chill beam arrangement. You've got much more moderate temperature being delivered out of the diffuser, and you have entire space coverage of diffusers. And then when you look at proper chill beam design, you look at the slow velocity coming into the occupied space, again, with the total goal of unified temperature and airflow distribution for better comfort. Acoustics, if you don't have any moving pieces and parts in the terminal device, there's nothing to make an additional acoustical sound. So it's very quiet. It's very accommodative for both learning and working environments. Here's a real world example of a chilled beam based system that delivered 35 dBA for background noise compared to a unfortunate unit vent, which was 55 dBA for background noise. So very big difference in acoustical levels. Maintenance, again, there's no moving pieces and parts. There's no fans, there's no motors, dampers, compressors that you need to address within the space, and there's no filters to maintain or change out within that device. From an architectural standpoint, both in renovation work as well as new construction. So in a renovation, you might not have the plenum space to renovate that with an all-air duct of 16-inch by or 18-inch duct routed throughout that plenum. You just couldn't do it. But in new construction, if you want to maintain that same ceiling height that I show of 9 feet, you might be able to reduce that physical structure by 1 foot to 2 feet very easily because of the minimal duct size that's only bringing in the ventilation air. So when you start talking about that reduction, we're talking structural steel, masonry, drywall, all sorts of building materials, and the net impact on a typical new construction can work its way on up to about $5 a square foot of savings. What type of applications are suitable for chilled beams? Certainly laboratories, government, educational, healthcare, limited plenum spaces or floor spaces, geothermal, heat recovery chiller applications. What might not be good solutions? Those areas where high humidity resides, or kitchens or bathrooms or cafeterias. And then maybe even high ceiling heights might not be a good solution as well. And what you see on the screen is suitable installations. Laboratories are a very good fit. Here you have an office space with exposed chill beam. And then here on the bottom, you have an educational facility and an office space being served by very traditional in-ceiling chilled beams. What you have here on the screen as well is plan drawings from a school renovation in Minnesota, where they integrated overhead chill beams in media rooms, conference rooms, corridors, and then displacement chill beams in classrooms. Another example, university in South Bend, Indiana, nursing hall renovation, where they integrated displacement chill beam into classrooms and office spaces, and then overhead chill beams in waiting room areas and common areas. So when you look at the system, and it's not just the chill beam by itself, it is the system and the integration of these components. For example, DOAS delivers a known quantifiable amount of outside air, doing a better job of dehumidification, ensures better thermal comfort. Chill beams deliver quiet, comfortable operation within the space. If you pursue the electrification approach, chill beams are well suited and qualify for tax savings. They're very efficient. The 20 to 35% example that I show there is very conservative, and compared to other well-designed systems, the first costs are very similar. Not to mention, if we do get to take advantage of the Inflation Reduction Act and tax credit, now it becomes a very attractive solution if you pursue that electrification path. So if you want more information about chill beams, both overhead, displacement style, please visit carsonsolutions.com. And with that, I will turn it back to Brandon.
Awesome. Thank you, Einar. And again, if you have more questions, you can reach out to your sales engineer as well. And next week's coffee break will be on system sizing and tools for gas, electric, and heat pump water heating. Thank you, everyone, for joining, and we'll see you next week.